Okay, the natural base E. When we're talking about the natural base E, it has a basis in a lot of things. One of the things is that if you notice on your calculator, and we'll look here first, you notice that where you have the log key on our calculator, that right below that there's an ln key. Okay? But also above the log key is 10 raised to the power of x. Above that ln key is e raised to the power of x. And so that e, we haven't used it before, but we're going to look at it today that it is involved with compounding interest in banks, and anytime they're calculating interest, it's used a lot, the letter E is. Well, if you remember the compound interest formula, which says that A equals P times 1 plus R over N raised to the NT power. Okay, remember we're working with that formula. Okay, we're doing compound interest, like if we're going to do it monthly or quarterly or daily, we've used that formula. Well, if we invested $1 at 100% interest, what would happen is that, and we compound it for n times a year, we would end up with a graph that looks like this one right here. And you notice what that graph does is that it moves as it comes up, and it gets closer and closer to that specific line there. And that specific line represents the number 2.7182818. Okay? And they use the letter E to represent that. And E is an irrational number just like pi is. But when E is used, it's used specifically when we're talking about compounding interest or something growing continuously. Okay? So it's growth that happens continuously, we use it. So it's just like, we have just like any other exponential function. We can write f of x equals e to the x, just like 3 to the x. And then the domain for that is going to be all real numbers in the range y is greater than 0. So this graph here of e to the x looks just like any other exponential growth graph that we've done. Well, because it's used so widely that they actually have to have an inverse for that too. And we're going to look at that today, that it's something called the natural logarithm that goes along with e to the x. But if we're compounding interest continuously, they use e as their value for the growth rate. So first of all, we're just going to look at, and we're just going to use our calculators for this. We're not going to be using get specific or anything like that with graphing it. So if we want to graph this, we're just going to go ahead and use our calculator to calculate some values, plug them in, and draw a graph. All right? So pretty simple. So on our calculator, we want, what we got here? We got e raised to the power of x minus 2 plus 1. So on our calculator, e is second and then the ln key. And then raising it to the power of x minus 2, or just 1x. And then plus 1. Okay. And then we can use our standard viewing window and see what that graph looks like. Okay. So it's growing quite rapidly. And so we can just plug in a few points from our calculator. And so we go to our table, and you can see how fast this is growing. It's getting very large very quickly. Okay. So we've got at -2, well, notice then. What do you notice about these numbers as I keep going farther into negative? So now, these are actually larger than 1. So that plus 1 there, the plus 1 actually takes our asymptote And instead of it being the x-axis, it's going to move it up to 1. So we'll plot a couple of these points. So we got -1, 1.04, so really close to 1, at 0, at 1, at 2 it's 2, 3 it's 3.7, and 4 it's 8.3, so that's then way up here. So our graph's going to look like this. So make sure you don't go below the line where x equals 1. Okay? We're not going to the x-axis. We're just going to 1. Because this 1 here was a vertical shift up 1, which makes it, changes the asymptote from the x-axis to the line y equals 1. So that exercise is just a matter of, can you put it in your calculator correctly, get a table, and graph it. Now, a logarithm with a base of e is called a natural logarithm, and it's abbreviated as ln rather than as log base e. So we will be using this symbol here, ln, instead of log base e. Natural logarithms have the same properties as all other logarithms because it's still just a logarithm with a base. It's just the base is e, which is 2.71828. Okay. So if we look at our graph here, here's a graph of our exponential growth function e to the x in blue, and the graph of the natural log of x in red, the inverse of it. So let's talk about inverses a little bit for a moment then. Just a little reminder, okay, that if I have 3 to the power, let's see if I'm calling that. If I have 3 to the power of x, the inverse of that would be the log base 3 of x. If I had 10 to the power of x, the inverse of that would be the log of x. So just a reminder that the inverse is basically taking it from exponential form to logarithmic form. So whatever the base is for the exponential, that's the base for my logarithm, the inverse of it. Okay? So here we have the graph of e to the x, the graph of natural log of x, its inverse. And they have the same properties of every other exponential function and logarithmic function. Logarithmic function, the domain x is greater than 0, the range is all real numbers. For exponential, the domain is all real numbers, and the range is exponential. But all the properties we talked about for the common logarithm or the logarithm in any other base applies for the natural logarithm, which has a logarithm of base e. So natural logarithm, we're using ln. Okay? So let's look at these, simplifying these expressions with e or natural logarithm. So if I have here example A, the natural log of e raised to the power of 0.15t, that's just like saying the log base e of e raised to the 0.15t power. Well, if that's the case, what's the answer to that? Yep, 0.15t. Because, yep, we have the same base. Okay? So whenever you see the natural logarithm, okay, why they use ln instead of nl, I don't know. Okay, but whenever you see the natural logarithm ln, that means it's a logarithm with a base e. So it's the inverse of e raised to the power of x. Now, letter B is a little bit different here. Okay? It's close, they're close to being inverses, But the problem we have is with this 3 right here in front. Okay? That free 3, okay, has to be moved to the exponent, so it becomes e to the natural log of x plus 1 raised to the third power. Whenever you are looking at same bases, anytime there's anything in front, okay, like this 3 here, that has become the exponent then. So then this answer would just be x plus 1 to the third, because my base here is e. Since it's natural log, the base there would be e also. So the other thing is that before we go on to letter C, is the fact if I do the natural log of e, that's just equal to 1, same as the log of 10 is equal to 1. Because these bases are the same, these bases are the same, so it would be equal to 1. So like for letter A, if I use the power rule and move the 0.15t to the front, then I'd have 0.15t times 1, which is just 0.15t. Same rules apply. Letter C, natural log of e to the 2x plus the natural log of e to the x. Since we have addition going on here, that means we're going to multiply e to the 2x and e to the x, which would be the natural log of e to the 3x, right? Since we're multiplying, same base, we add the exponents. And now I can simplify this. Since my bases are both e, this just equals 3x. Okay, the formula for continuously compounding interest is A equals PE raised to the power of RT, which we call it the PERT formula. Okay? And it's used whenever we're going to continuously compound interest. So this is what you really want your bank to do for you. Okay, if you're putting money in the bank, you want them to compound interest continuously. You don't want that quarterly or monthly stuff. It doesn't, you get decent returns on it, but the more often they compound the interest, the more money you're going to get. And so we want it to be compounded continuously, which is usually what most banks do for you. The problem is that our friends, the credit card companies, also like to do the same thing. So that's why it's very important to pay off your, if you're going to use a credit card, pay it off very quickly if you can. Or get one with 0% interest for a while and then pay it off, though, before the interest is. So it says, what is the total amount for an investment of $500 invested at 5.25% for 40 years and compounded continuously? So we're going to use we'll use our PERT formula, where P is our principal amount, E is our interest rate, or not the interest rate, but our growth. 5.25%, that's going to be our value of R, except we're going to change it to a decimal. And then T is 40 years. So A is equal to 500 times E raised to the power of 0.0525 times 40. And we can just put that right into our calculator then. So on our home screen, 500, and then E is second natural log, and raised to the power of 0.0525 times 40. So that means that we will have now approximately $4,083.08. I guess that's not too bad. Just how many of you think you wait 40 years to spend some money? Leave it in a bank for that long? Probably not. I wouldn't. Okay. All right. Here's another one. Use the formula A equals PE to the RT to compute the total amount of an investment of $4,500 at 5% interest compounded continuously. So we're always looking for compounding continuously is what we're looking for to use the PERT formula. And as long as I've got that, I'm good. So you have to remember that we have, and we'll talk about this in a second, is that, so we use this one, A equals 4,500, E raised to the power of 0.05 times 6. So we would have approximately 4,500 E raised to the 0.3 power, right? And so $6,074.36. So we've looked at 3 different ways of compound interest. We looked at, or of growth and decay. We had A equals P times 1 plus or minus R raised to the power of T. Okay. And we used that when we were doing either this shows growth. You know what, let me go to a different page here. Oh well. So we've looked at, yep, I got it. Okay. Growth or decay with this formula here. So that's something that's compounded annually, okay? It's not monthly or daily or yearly, okay? So compound growth or decay looks like that. We have compound interest, which is A equals P times 1 plus R over N raised to the power of NT. Now the compound interest is similar to the growth and decay. The only difference is that it might be quarterly or monthly or daily, etc. Okay? And that's where N comes into the play. N actually tells us how many times a year then we're going to compound interest or calculate the interest. And then if we are going to compound interest continuously, did I spell that right? There's not 2 U's there, is there? Compound interest continuously, then we will use the PERT formula. Okay. So during the course of this chapter, we looked at all 3 of those. Okay. If it's growth or decay and it's just an annual thing, then we're either going to add the interest rate or subtract the interest rate from 1. If it's compound interest, compounded quarterly, monthly, daily, whatever it is, as long as it's not yearly, then we're going to use this one where n actually represents how many times a year. And if we're doing it continuously, then we use this PERT formula. All right. Okay. All right. So last thing, half-life. The half-life of a substance is the time it takes for half of the substance to break down or convert to another substance during the process of decay. Natural decay is modeled by this function below. N of t equals n sub 0, e raised to the power of negative kt. Now these get a little bit, take a little bit of work to do these problems. N sub 0 represents our initial amount that we're using. K is what we call the decay constant. N of t is the amount remaining at the end, and t is your time. What happens in some of these problems that we're going to end up working with is the first thing we have to do is find the decay constant before we can find the actual value we're looking for. So here we have a paleontology application. It says plutonium-239 has a half-life of 24,110 years. How long does it take for 1 gram sample of plutonium-239 to decay to 1/10 of a gram? So the first thing we've got to do is we've got to find the decay constant for plutonium-239. And we know that the half-life is 24,110 years. So what does that tell us? What does half-life mean? Learned it in science, right? Okay. All right, we've talked about it, but we learned it in science too. That half-life is how long it takes to go from the amount you start with till half of it is remaining. Okay? So we have a time frame here of 2,000 or 24,110 years. So if we start with 1 gram, okay, and we don't know K, but we do have a time we're working with, 24,110. Okay. Well, if I start with 1 gram, and the 24,110 is my half-life, right? That means then that's how long it's going to take me to get half that amount. All right, so we're not using the 0.1 yet. I wish that fly would go away. I know. I haven't found a way to kill him yet. He keeps escaping me. So we have to solve this equation. So let's simplify the way it's written first of all. So we got 0.5 equals e to the negative 24,110 k. So we have an exponential equation. Can I write e and 0.5 with the same base? Okay. We can't do that. Okay. So what we're going to do is we're going to take the logarithm of both sides then to find the value of k, except for since we're using the base of e, instead of using logarithm, we're going to use the natural logarithm. So we'll do the natural logarithm of 0.5 equals the natural logarithm of e raised to the negative 24,110 k power. Now the really nice thing about using the natural logarithm is, what did we say the natural log of e is? The natural log of e is 1. So what's nice about this is the natural log of 0.5 then is just equal to negative 24,110 k. because we have this instance where where these two bases are the same, which means it just equals the exponent. And so to find this answer, we just divide both sides by negative 24,110. And we're going to get a really small number. Okay, that number's got an E. What does that tell me? Yep, good. Got to move the decimal 5 places. So K is going to be equal to, or approximately, put that in there, 0.1, 2, 3, 4 zeros, and then 287. Now that we have the decay constant, then, we can now solve to see how long it takes to get to 1/10. We know that it takes 24,110 years to get to 0.5, but we need to find out how long it takes to get to 0.1. So we're going to use the same formula, except we're trying to get to 0.1 instead of 0.5. So we're starting with 1, and then we have e raised to the power of, now we know k, negative 0.1, 2, 3, 4, 287 k, oops, t. So once again, we take the natural log of both sides. Now, before we actually finalize the answer to this question, is my answer going to be more or less than 24,110? Is the answer going to be more or less than 24,110? Okay. How many people think less? Okay. All right. You guys all think it's going to be less. Okay. Now think about it for a second. It took 24,110 years from it to go to 1 to 0.5, right? So if we're reducing it farther than 0.5, we're reducing it down to 0.1. That means it's going to take more than that. Okay, it's not less than that. It's going to be more than that. So divide by negative 0.000287. And let's see what we get. Natural log 0.1 divided by negative 80,229 years. A little bit longer, wasn't it? So approximately 80,229 years. So the fact is that it is going to take a lot longer for that to happen.